when x is equal to 2, that's going to be log base 3 to the power 4, which is 1.26. And the last one, when x is equal to 3, that's going to be log base 3 to the power 2 times 3, which is 6. Log base 3 to the 6 is 1.63. I'm going to draw both of them on the same set of axes. That's my x-axis, that's my y-axis. The first graph I'm going to draw in red is the graph of f of x. Now the standard log graph, that is a standard log graph. When x is equal to 1, it's going to pass through y value of 0. When x is equal to 2, it's going to be positive 0.63, which is going to be somewhere over there, and well, a bit higher actually. And when x is equal to 3, it's going to be 1. So basically my log graph is going to look like this, the inverse of my exponent graph. In black, I'm going to draw the graph of g of x. When x is equal to 1, y is going to equal 0.63. When x is equal to 1, that's over there, y is going to equal 0.63, which is somewhere up here. When x is equal to 2, y is going to equal 1.62, which is over there. When x is equal to 3, y is going to equal 1.63, which is over there. Let's look at it a little bit passing through the 0 mark. In order for that to be log base 3 to the power 1, x would have to equal a half. So do you notice what's happening with this graph? It's not intersecting at the same point, but it is going to sort of flatten out and follow that direction. So it is going to eventually intercept the f of x graph and then move above it, or sort of go past it. And that is the graph g of x is equal to log base 3 2x. The next graph we're looking at is f of x is equal to 2 times x minus 3 squared minus 32, and g of x is equal to 2 times 2x minus 3 all squared minus 32. What I'm going to do with this graph here, I'm going to start off by saying y is equal to 2 to the power 2 times x minus 3 to the power 2 minus 32. With this graph over here, what I'm going to first start by doing is looking at my turning point, which is, remember, my standard parabola is ax minus p squared plus q, which means that my turning point is at pq. My turning point in this graph is going to occur at x is equal to positive 3, y is equal to negative 32. That's where my turning point is going to be. My x-intercept happens when y is equal to 0. That means that 2 times x minus 3 all squared minus 32 is equal to 0. That means that 2 times x minus 3 all squared is equal to positive 32. That means that x minus 3 all squared is equal to 16. That means that x minus 3 is equal to positive or negative square root of 16, which is plus or minus 4. That means that x is equal to 3 plus 4, which is 7, or 3 minus 4, which is negative 1. To get my y-intercept, that's when x is equal to 0. That's going to be 2 times 0 minus 3 squared, which is positive 9. 2 times 9 is 18. 18 minus 32 means that my y-intercept happens at 18 minus 32. I'm just going to work that out on a calculator because my mental maths is really bad. Y is equal to negative 14. Alright, now I'm going to sketch this graph before I do anything else. And let's see if we can do the transformation immediately. Firstly, I know that my let's just write this over here. Turning point happens at 3, negative 32. My x-intercepts are at 7 and negative 1. My y-intercept is at negative 14. And that's all the information that I need. We're now going to sketch this thing. That's my x-axis, my y-axis. Remember that my turning point happens at x is equal to positive 3, y is equal to negative 32, so it's way down there. Two x-intercepts are one at x is equal to positive 7, the other one at, let's make that somewhere over there, x is equal to positive 7, y is equal to negative 1, and my y-intercept is at negative 14, which I'm going to sketch in now. So it's negative 14, very inaccurate graph, but it's okay. And that's my graph f of x. Now, the reason I did this graph last is because we're now going to look at what effect does that 2x have on it. Now remember that in all of our graphs so far, the minute we put a value, a whole number, in front of the x, it sort of contracted the graph or made it a bit tighter. If we put a fraction in front of it, it made it a bit wider. With this being a 2, I'm guessing that my graph is going to still turn at the same point, but or at nearly the same point, but it's basically going to become a lot tighter. It's going to sort of go in. Let's see if that holds true. The first thing we're going to be looking for is our turning point. Now our turning point, remember, is x minus p squared plus q. That is a slight problem. Let's first multiply this out. 2x minus 3 all squared, that's going to give me 2 times 4x squared minus 12x plus 9 minus 32, which is going to give me 8x squared minus 24x plus 18 minus 32 is minus 14, and that's what g of x is effectively equal to. To get my turning point, I'm first going to have to do, because it's in the form ax squared plus bx plus c, which is now a slightly different form than ax minus p squared plus q. Because it's in this new form, we're going to have to start by getting our axis of symmetry. Our axis of symmetry is given by minus b over 2a, which is minus 24, which is positive 24, over 2 times a, which is 2 times 8, which is 16. 24 over 16 can be simplified to become 6 over 4, which can further be simplified to be 3 over 2. So my axis of symmetry is 3 over 2, as opposed to my original axis of symmetry, which was x is equal to positive 3. So my new axis of symmetry is going to be, it's actually going to be exactly half of my original axis of symmetry. So my guesstimation on the graph is a bit wrong. The next thing we're going to look at after our axis of symmetry is we are going to look for our turning point. Our turning point, remember, happens at our axis of symmetry. When x is equal to 3 over 2, that's going to be 8 times 3 over 2 squared. 8 times 3 over 2 squared minus 24 times 3 over 2 minus 14, which is equal to negative 32. So my turning point is still at negative 32. So my turning point is still over there, except my graph has a new axis of symmetry. To get my x-intercepts, we're going to make y is equal to 0. That means that 8x squared minus 24x minus 14 is equal to 0. That means that 4x squared minus 12x minus 7 is equal to 0. Can this be factorized? 4 times 7 is 28. Are there factors of 28 that give us 12? We know that 2 times 14 is equal to 28, so yes, there are. We need to get to 14 minus 2. 14 we are going to get from the 7. Because it's a prime number, it can't be broken up. So it's going to be 7 times 2x to give us 14x plus 14x minus 2x is going to give us, oh, we need to get minus 14. Whoops. Minus 14 plus 2x is minus 12x. That's going to give us minus 7. That means that our two x-intercepts are going to be 1, where x is equal to negative 1 over 2. So that's going to be over there. And the other x-intercept is going to be at 7 over 2, which is going to be somewhere over there. That means that our graph looks very much like that. You can see that it has contracted inward because of that 2, and the turning point has moved slightly to the left. But essentially it's still the same graph, it's just been shrunk inward. And if my graphs were any accurate, you would have found that this graph does always sort of stay almost under or inside the red graph, the f of x graph. The next graph we are looking at is f of x is equal to 3 over x plus 1 and g of x is equal to 3 over 2x plus 1. I'm not going to draw this one using the table method. I'm going to draw this one using logic. Now, what's happened? We've got a hyperbola, a fraction graph, alright? But we've transformed it. We've said x plus 1, which means that we've moved our asymptote and we've moved our entire graph minus 1. X cannot ever equal negative 1. Y cannot ever equal 0. So that's still our asymptote, that's fine. That means that our graph, and because the 3 is positive, the original f of x graph is going to look a lot like that. And that's the standard hyperbola f of x. By the way, it's always in the positive and in the negative quadrant. Now the next one we have is g of x, which is equal to 3 over 2x plus 1. Now let's look at where the asymptote is going to be. Firstly, the new asymptote is going to be where x is equal to negative a half, not negative 1. So what's happened? We've just basically, again because of the 2, it means we've just contracted our graph slightly. That's going to be over there, and well, actually that's supposed to go over there, never touching the asymptote and crossing the f of x graph at a point. And that's all that's happened. It's just been contracted in, and because of the fact that it's been contracted in, the asymptote has moved slightly. In the negative axis it's contracted more sort of out than in. You can do the table method to work this out. You're welcome to do that. You will find that you'll get the same graphs. In fact, I'd suggest you do the table method just to test the accuracy. We are now going to look at trigonometric graphs. Trigonometric graphs are slightly trickier than the other functions we were looking at, especially with regards to expansions and contractions. We will use the example of sine of x and we will expand on that. The next one we're going to be looking at is y is equal to sine of 2x. Now the table I've started drawing is a standard table that we normally use for trigonometric graphs: 0 degrees, 90 degrees, 180 degrees, 270 and 360. I'm only looking at this in the positive axis. When x is equal to 0 degrees, that's going to be sine of 0, which is 0. When x is equal to 90 degrees, that's going to be sine of 2 times 90, which is sine of 180 degrees, which is 0. When x is equal to 180 degrees, that's going to be sine of 2 times 180, or sine of 360, 0. When x is equal to 270 degrees, that's going to be sine of 2 times 270, which is the same as sine of 540. Sine of 540 is equal to 0. 360, sine of 270 is equal to 0. Now there is a slight problem with this. More than a slight problem, there's a huge problem with this. If we're looking at our x values of 90, 180, 270 and 360, notice that all the points of intersection are 0. Is it possible that it's just a straight line, a straight horizontal line? No, it's not. Now look at this. What if I add in values in between 0 and 90? 45 degrees. That's going to be 45 degrees times 2, which is 90. Sine of 90 is 1. Between 90 degrees and 180 degrees is 135 degrees. 135 times 2 is 270. Sine of 270 is negative 1. Between 180 and 270 is 225. Sine of 2 times 225, which is the same as sine of 450, is equal to positive 1. Sine, the next one is between 270 and 360, which is 315. 315 times 2 is 630. Sine of 630 is negative 1. Now let's try and draw this. At 45 degrees, my y value is 1. At 90, it's 0. At 135 degrees, my y value is negative 1, 0. At 225, it's positive 1. At 270, it's 0. At 315, it's negative 1. At 360, it's 0. Bit distorted graph, but you get the drift. This is between 0 and 360 degrees. Notice all we've done is the standard graph should have come like this, drop down over there, go to negative 1 over there, and go back to 0 there. That would have been the standard sine of x graph, but the graph we've drawn is sine of 2x. Notice that it's double. We've sort of taken the standard sine graph, we've contracted it, and we, instead of having one wave, we are now having two waves. So that 2 means that we are doubling it. If that were sine 3x, we would have triple as many, 3 times as many. If it was sine of a half x, this sine graph would be just a half. Or sine of a third, we'd only be looking for a third of the sine graph. Have a go at the following examples. Press pause on your DVD player, and when you return, we'll go through it together. The next graph we're looking at is sine of 3x. Sine of 3x, I told you to draw it for the interval negative 180 degrees all the way up to positive 180. The way I drew my graph with intervals of, I included 30 degrees, 60 degrees, 120 degrees, 150 degrees, and in the negative also negative 30, negative 60, negative 120 and negative 150. Now the way this sine graph is going to go is, because it's 3x, it means that there's 3 times as many graphs. So it's going to peak at 30, drop at 60, negative 1 at 90, at 120 it's going to be 0, at 150 it's going to peak, and at 180 it's going to be 0. That means that our graph is going to look like this. 3 times, basically 3 times as many graphs, or 3 times as many waves as the standard sine graph. Oh, and don't ever forget to label it. The next one we're looking at is g of x is equal to a half cos x. Now the half is in front of the cos x. When we've got 0, cos of 0 is equal to 1, but it's 1 times a half, which is a half. 90, cos of 90 is 0, times a half is 0. Cos of 180 is negative 1. Negative 1 times a half is negative a half. Cos of 270 is 0, times a half is 0. Cos of 360 is positive 1. Positive 1 times a half is a half. Cos of negative 90 is 0, times a half is 0. Cos of negative 180 is negative 1, times a half is negative a half. Cos of negative 270 is equal to 0, times a half is 0. Cos of negative 360 is equal to positive 1, times a half is a half. So basically our cos graph is now going to look like this. Notice all that's happened is that we've got a half in front of the cos of x. The standard cos of x graph, I'm going to draw that in red. The standard cos of x graph should have gone like that. Except now, because we have a half in front of it, all that's happened is each peak and each trough has been shifted inward. It still has the same 0 points. And that's the graph g of x. The next graph we're looking at is tan of a half x. Now when we're doing this one, remember that this is a tan graph, and a tan graph has got standard asymptotes at negative 90. It's supposed to have at negative 90, at positive 90, and again at positive 270. Because we cannot have x is equal to, we cannot have tan of 90, tan of negative 90, or tan of positive 270. The problem in this case though is we actually can. Tan of 90, or not tan of 90, but if x is equal to 90, that's going to be tan of a half times 90, which is tan of 45, which is equal to 1. But what happens when x is equal to 180 degrees? When x is equal to 180 degrees, that's going to be tan of a half times 180, which is tan of 90. Tan of 90 is undefined, hence 180 degrees is a new asymptote and not 90. And the same will happen in the negative axis at negative 180, which we don't have here, but at negative 180 will be the new asymptote that it cannot equal. 90, the positive 90 as well as the negative 90, is going to be where x is equal to either negative 1 or y is equal to positive 1. That means that our graph is going to look very much like that. So instead of it being the small interval between negative 90 and 90, our sort of propeller looking graph is going to be between the negative 180 and positive 180, and the same thing will happen past 180, in that it will take the same shape, and it will be 0 at 360 degrees, and it will carry on, and it will have an asymptote beyond that. And the same thing will happen in the negative axis. The reason for this is that it's 10 over half x, which means that we've expanded our graph out. If it was, for instance, 10 of 2x, our asymptotes would then not be at negative 90 and 90, but rather at negative 45 and 45, and our graph would come closer in. The fourth example read j of x is equal to negative 2 cos 3x. Now this is a number of different transformations that are all happening at once. Firstly, cos 3x means that we have triple the cos graph. So instead of it's going to peak at x is equal to 0 degrees, but when x is equal to 30 degrees, that's going to be cos of 90, which is equal to 0. 0 times negative 2 is 0. Now that negative 2 has to come into play as well. When x is equal to 0 degrees, that's going to be cos of 0, which is equal to 1. Multiplied by negative 2 is going to give us negative 2. Let's see if we can find a pattern here. When x is equal to 30 degrees, it's going to be cos of 90, which is 0, times negative 2, which is 0. When x is equal to 60 degrees, that's going to be 60 degrees times 3, which is 180 degrees. Cos of 180 degrees is negative 1, multiplied by negative 2 is going to give me positive 2. Negative times a positive is negative. Negative times a negative is positive. When x is equal to 90 degrees, that's going to be 90 times 3, which is 270. Cos of 270 degrees is equal to 0. 0 times negative 2 is 0. When x is equal to 120 degrees, 3 times 120 degrees is equal to 360. Cos of 360 is equal to positive 1. Positive 1 times negative 2 is going to give me negative 2. Now let's look at this graph over here. This graph is basically going to be doing this here. Do you see what's happening? We've increased the cos graph. We've got 3 times as many cos waves, but its amplitude and its trough is at 2 times greater, but because of the negative it's flipped around, so instead of it being up there, it's now down there, and this is going to give us the cos This is going to give us the cos graph that we are looking for, j of x. I'm going to sketch, after I'm done with this, I'm going to sketch the standard cos graph, and I want you to see what a huge transformation it is. Remember, I said that there are 3 transformations that have happened in one. Now the standard cos graph, I'm going to draw it in red. The standard cos graph should have done that. Oops. Oh, no, that's right. That should have been the standard cos graph. What's happened? Firstly, we've made it 3 times as many. Then we've increased the height and the drop to 2 and -2. Then we flipped it around. We are now going to look at graph flips. There are 2 types of flips. The first is around the x-axis and the other is around the y-axis. Let us use some examples to illustrate. We are now going to look at flip graphs, or rather flipping it around the axis and all of that. The first one I'm looking at is f of x is equal to 3x plus 1. Easy graph to draw. When x is equal to 0, y is going to equal 0 plus 1, which is 1. When y is equal to 0, that's going to be 3x plus 1 is equal to 0. That means that 3x is equal to -1. That means that x is equal to -1 over 3. I'm going to draw my axis, and I'm going to start by sketching that graph. X-axis, y-axis. It's through the point x is equal to 0, y is equal to -1 over 3. Let's make that down there. And when y is equal to 0, x is equal to negative, when y is equal to 0, x is equal to -1 over 3, that's over there. And the other point is when x is equal to 0, y is equal to 1, that's going to be over there, which means that this graph is going to look like this. And that's the graph f of x. The next one we're looking at is g of x is equal to 3 times -x plus 1. Notice the difference there is that we've now made our x value negative. When x is equal to 0, y is going to equal 1. That means it's still going to cut through that point. Except when y is equal to 0, that's going to be -3x plus 1 is equal to 0, which means that x is going to equal positive 1 over 3, which is going to be over there. That means that this graph has been flipped that way. And that's the graph g of x. The next one we're looking at is when h of x is equal to minus 3x plus 1, 3x plus 1 in brackets. Basically, we've put a negative in front of that, so it's almost as if we've put a negative in front of the y. To get rid of the negative in front of the y, we divide through by a negative, which makes that negative. When we put a negative in front of the y, we have this happening. When x is equal to 0, y is going to equal -1. That means that the y-intercept is now going to be at -1. And when y is equal to 0, that means that -3x If I multiply that negative in, negative 3x, negative 1 is equal to 0. That means that x is equal to negative 1 over 3. Or rather, x is equal to negative 1 over 3. That means that that is going to give us this graph over here, which is the graph, slightly inaccurate, hx. Now, I want you to look carefully at what transformations happened from the original f of x graph. When we went from f of x to g of x, we made the x value negative, which means that we flipped our graph around the y-axis. Take a look at just the blue and the red graphs. Look at that, about the y-axis. Didn't we just take this f of x graph and we turned it around that way? We flipped it around the y-axis, which made the x values negative. Now look at the blue graph again, the f of x graph. When we made y negative, or rather this whole expression negative, which is the same as making y negative, we flipped it around the x-axis. We took our original f of x graph and we flipped it to make h of x. We flipped it around the x-axis. So the rules are, when we are flipping about the y-axis or around the y-axis, the x values become negative, or if it is negative x values, it will become positive. And when we are flipping about the x-axis, the y values become negative, or if they are already negative, they become positive. The next example I gave you to do started off with f of x is equal to 2 to the power x. This is an exponential graph, so the standard exponential graph is going to look like that. And that is the graph f of x. And it crosses through 1. The next one we're looking at is g of x is equal to 2 to the power negative x. What has happened? We've put a negative in front of the x. The x's positive value has become negative, which means that if the x's value has become negative, it means we are flipping it around the y-axis, which means that this graph will look very much like this. It is the f of x graph flipped around. It's still going to cut through 1. The last graph, h of x is equal to negative 2 to the power x, means that it's almost as if our y values, of the y's positive value has become negative. That means that we've taken our standard graph and we've flipped it around the x-axis. If we're flipping it around the x-axis, our graph is going to look like that. And that's the graph h of x, which is the flip of f of x. And that's not going to pass through x is 0 and y is 1. That's going to pass through x is 0 and y is negative 1. The next graph I gave you to do read f of x is equal to 5 over x minus 1. Now 5 over x minus 1, you can see immediately that this is going to be a hyperbola graph. I'm just drawing my axis in over there. Hyperbola, but it's been shifted 1 unit to the right. That means that my asymptote is at x is equal to 1. That's the asymptote, x is equal to 1. Now my standard graph, 5 over x minus 1, my standard graph is going to go over there and over there. And that's my graph f of x. The next graph we're looking at, g of x, is equal to 5 over minus x minus 1. What's happened to this? 5 over minus x minus 1 means that we've put a negative in front of the x, which means that we are going to be flipping it about the y-axis. One problem with this is we are flipping our entire graph, the whole graph, including the asymptotes, around the y-axis. That means that we are going to have a new asymptote of x is equal to -1, and our graph, it's been the entire graph flipped around the y-axis, which means that our new graph is going to be over there and over there. Notice what a weird one this seems to be. We've taken the graph and we've flipped it around the y-axis. Actually, this one shouldn't be over there. This one should be cutting at that same point over there. And that is the graph g of x. The next graph we're looking at is h of x. Notice that h of x has the negative sign by the 5, which is almost as if we've made our y value negative. So we've taken our normal f of x graph. Remember, we're flipping the f of x graph. The g of x is one of the flips or transformations of the f of x graph, but when we work with the h of x graph now, we're still looking at that original graph, and we're flipping it about the x-axis because the y value has changed. About the x-axis means that our new graph still maintaining the same asymptotes as the original graph, the red graph, except it's now been flipped about the x-axis, and that's the new graph h of x. Notice how h of x is fairly similar to g of x, except g of x is basically f of x shifted 2 units to the left. Think about that one carefully. We are now going to look at the inverse. As you will remember from the tutorial on the exponential and logarithmic graph, that the logarithmic graph was the exact inverse of the exponential graph. We are going to apply that same concept to the other functions. An inverse is when the x values and y values simply swap. Let us have a look at some examples. The first one I gave you to sketch of the inverse graph, I said draw the graphs of f of x and its inverse on the same set of axes. F of x, if we're going to sketch this, we only need 2 points. Firstly, when x is equal to 0, y is going to equal -2, and when y is equal to 0, x is going to equal +2/3. The inverse graph, now the original graph reads y is equal to 3x minus 2, which means that the inverse graph x is equal to 3y minus 2 means that 3y is equal to x plus 2, y is equal to x over 3 plus 2 over 3. If I do my table, small little table for this one, when I have an x value of 0, my y value is going to be 2 over 3. And when I have an x, or rather a y value of 0, x is going to equal positive 2. If I try and sketch this on a set of x's, that's my x-axis, y-axis. Firstly, of f of x, which I'm going to sketch in red, when x is equal to 0, y is going to equal negative 2. And when y is equal to 0, x is going to equal 2 over 3, which is going to be somewhere over here, which means that this graph is going to look like this. And that is the graph f of x, the original graph. The next graph we're going to be looking at in blue is the inverse graph. When x is equal to 0, y is equal to positive 2 over 3, which is going to be over there. And when y is equal to 0, x is going to equal positive 2, which is going to be over there, which means that this graph is going to be drawn like that. And this is the inverse graph of f of x. A very, very important thing, firstly, my graphs are never accurate, but if I have to draw in a line y is equal to x through the origin, well, y is equal to x always goes through the origin, my graphs are flipped around the line y is equal to x. Obviously, like I say, I haven't drawn it very accurately. It should be a little bit higher, and that point of intersection should fall on that line. The next example I gave you to do on inverses read f of x is equal to 9x squared minus 4. Now, in order to sketch this graph, it is going to be a little bit trickier. Firstly, we are going to need our turning points. Our turning points, or rather first, our axis of symmetry happens when x is equal to minus b over 2a. We don't have a b value, ax squared plus bx plus c. That means that our axis of symmetry is on 0. That means that our turning point happens at x is equal to 0, y is equal to negative 4. That's where our turning point happens. We then look for our x-intercepts, which means that y is equal to 0. 9x squared minus 4 is equal to 0. 9x squared is equal to 4. X squared is equal to 4 over 9. X is equal to positive 2 over 3 or negative 2 over 3. Sketching that on a graph, we're going to find that firstly our turning point is when x is equal to 0, y is equal to negative 4, so that's somewhere over there. Two x-intercepts, negative 2 over 3 and positive 2 over 3, and a y-intercept of negative 4, which is the same as our turning point, and it's a smiley face graph because it's positive 9x squared. And that is the graph f of x is equal to 9x squared minus 4. Now we are going to draw the inverse. Now don't do what I'm doing. F dash x is going to equal, or rather the inverse of f of x is going to be x is equal to 9y squared minus 4, and you can do all of those fancy calculations, or you could just take your graph and flip it around that line, around that blue line. If I flip my graph around that blue line, what's going to happen? It's going to intercept at those 2 points, and that's going to be my new graph. By the way, this new graph is not a function. The inverse graph is not a function. because if I use the vertical line test, it will cut it twice. And it will intersect it at those 2 points, and that's the line x is equal to y, or rather y is equal to x. All we've done is we've flipped it around that line. And that finally brings us to the end of the 7th functions tutorial, the basic sketch and transformation. Go through the exercise that I've left for you in the workbook. Make sure that you are able to do all of it, and you will find the next 2 tutorials quite easy and fun.